Welcome to the second lecture on properties of triangles. Let us spend the next few minutes in recapping and revising what we had done in the first lecture. So, in this lecture also and in the subsequent lectures, we will be discussing the properties of triangles. So, as you can see here, so we denote the vertices of the triangles by the uppercase letters A, B and C, and for this angle shall be denoted by the same letter as that used for the vertex corresponding to this angle, which is A itself, and this angle will therefore be B and this will be C. So, for the angles we will be using the uppercase letters. For the lengths of the side, so the length of the side that is opposite to angle A will be denoted by, so the side which is opposite to angle A is this side BC, and we will denote it by lowercase a, and similarly the side AC is opposite to the angle B, and therefore its length will be denoted by lowercase b, and similarly the length of this side will be lowercase c. The area will be denoted by this delta symbol, and frequently we will be coming across something known as the semi perimeter, which we will be denoting by S, and this semi perimeter is essentially half of the perimeter of the triangle, which is A plus B plus C over 2. So, yesterday we discussed the sine law and the cosine law. So, let us just revise it today also. So, the sine law says that the ratio of the length of a side to the sine of the angle opposite to that side is a constant. So, A upon sine A is B upon sine B is C upon sine C. The cosine law, which is stated here and which we also derived in yesterday's class, it gives us formulas for, or basically the relation between the cosine of angles of the triangle and the length of the sides of the triangle. We then also derived the formulas for the sine and cosine of the half angles of the angles of a triangle. So, for example, we derived this particular formula that sine A by 2 is square root of S minus B times S minus C over B C, and similar thing we did for cosine of A by 2, and of course, then the others can be similarly written. So, for example, sine of angle B over 2 will be square root of S minus A into S minus C over AC. The cosine of B over 2 will be square root of S into S minus B over AC, and similarly sine of C by 2 is square root of S minus A into S minus B over AB, and cosine of C over 2 is square root of S into S minus C over AB. So, we did all of this in the last lecture, and then towards the end of the last lecture we derived this formula which gives us the area of the triangle in terms of the lengths of the sides of the triangle, and it is known as the Hero's formula. We started a new discussion on the circles that are associated with a triangle, and the first type of circle that we discussed was the circumcircle. So, we said that if we have any triangle, for example, the triangle ABC shown here, we said that if we consider the perpendicular bisectors of all the three sides, and suppose that all of them meet at this point O, then we showed that this distance OA, OB and OC are all equal. So, these distances are all equal, and therefore, what that means is that the circle which touches all these 3 points A, B and C will have O as the center, and that particular circle is called the circumcircle. So, because A, B and C are 3 non-collinear points, there is exactly one unique circle which on which all the 3 points A, B and C are going to lie. The radius, which is OB of this circumcircle, is called the circumradius, and we shall denote it with a uppercase R, and the formula for the circumradius is it's equal to the product of the lengths of the sides of the triangle divided by 4 times the area of the triangle, and this also happens to be equal to half of the ratio of A upon sin A. So, this was the last thing that we had derived in the previous class. So, in today's class we are going to continue our discussion on the circles associated with a triangle. So, the next type of circle that we are going to discuss is called the incircle or the inscribed circle. So, the incircle or the inscribed circle is the unique circle which is entirely inside the triangle, and for which all the 3 sides of the triangle are tangents, or basically this circle touches the 3 sides. Each of the 3 sides is at exactly one point. So, let us suppose that we have this triangle A B C over here, and let us say that we bisect this angle B. So, let us say that this dotted line here is the angular bisector of angle B. So, this angle here is B by 2, and then we also construct the angular bisector of angle A. So, the angular bisector of angle A, so let me show it with a red line. So, both these angular bisectors are going to intersect at a point, let us say here, and I will mark it as O, and then from O we drop a perpendicular. So, from O, let us say that we drop a perpendicular to the side AB. So, let this black dotted line be the perpendicular from the point O to the side AB of the triangle, and let us say that this perpendicular intersects the side AB at this point D, shown in black uppercase, and then let us also drop a perpendicular from this point O onto this line BC. So, this is the other perpendicular, and let me call the point where this perpendicular intersects the line BC. So, I will call it as the point E. So, next let us focus on these 2 triangles. So, we will focus on the triangle BOD and the other triangle. So, triangle BOD is this right angle triangle, and the other triangle is triangle BOE. So, that is also a right angle triangle, and it is easy to see that First of all, they have a common side OB, and then the angle BEO, which is 90 degrees, is equal to the angle BDO. And lastly, since this blue dotted line is the angular bisector, it follows that this angle and this angle are both equal to b by 2. And from there it follows that these two triangles are congruent. And because these two triangles are congruent, it follows that OD must be equal to OE. So, OD is equal to OE. And a similar thing can be shown if we drop a perpendicular from this point O onto this line AC, and let us say that this perpendicular intersects the line AC at point F. Then by taking considering the triangles AOD, so triangle AOD and the other triangle is AOF. So, in a similar manner we can show that even these two triangles are congruent, and because they are congruent, it follows that OD is equal to OF. But since OD is also equal to OE, it follows that OD, OE and OF are all equal. They are all equal. Since these 3 points D, E and F are not collinear, they are not collinear, we can construct a circle. So, there will exist a unique circle which passes through all these 3 points. So, essentially these 3 points D, E and F are going to lie on the circumference of a unique circle, and that circle, let me draw it in green. So, this is the circle, and it is clear that the because OD is equal to OE is equal to OF, it is very easy to see that the point O is actually the center of this circle which I have drawn in green, and in fact OD is nothing but the radius of this circle, which I denote with a lowercase r alphabet. This circle touches the triangle ABC at exactly 3 points D, E and F. This circle is further completely inside the triangle ABC, and that is why it is called the inscribed circle, or sometimes it is also called as the incircle. And of course, wherever it touches, so it is clear also that because this angle is 90 degrees, at this point D, the line AB is a tangent to the incircle at the point D. Similarly, the line AC or the side AC of the triangle ABC is a tangent to the incircle at the point F. Our next objective is to find an expression for the radius r of this incircle in terms of the lengths of the sides of the triangle ABC. So, for that, let us consider this triangle here. So, let us consider the triangle BOD. So, what we can see from this triangle is that, first of all, it is a right angle triangle, and the other thing we saw was that both BOD and BOE were congruent. So, we'll try to use something known as the projection formula, and which is very easy to see. So, we will focus on the triangle BOD, and the other triangle that we will consider is triangle AOD. Now, we know that this entire length, this AB is equal to lowercase c. So, we know that this C is actually equal to BD plus AD, but BD is one of the sides of the triangle BOD, and in fact, since this half angle is B by 2, we know that tan of B by 2 is equal to R upon BD, from which it follows that BD is equal to R upon tan B by 2. Similarly, if we consider the other triangle AOD, so let us consider the other triangle AOD, and there we see that this length AD, so AD so just as we wrote the tan formula here for the triangle BOD, in this triangle we see that tan of A by 2, because this half angle is A by 2. So, tan A by 2 is equal to R divided by AD, and therefore, AD is equal to R divided by tan of A by 2. And now, if we substitute these expressions for BD and AD into this particular equation, where C is equal to BD plus AD. So, if we do that substitution, then what we get is C equals R into 1 upon tan of A by 2 plus 1 upon tan of B by 2. So, we take this over to the next slide. So far what we have got is that C is equal to R times 1 over tan of A by 2 plus 1 over tan of B by 2, and therefore, from here it follows that the radius of the in circle R is equal to C upon 1 over tan A by 2 plus 1 over tan B by 2. And here we will have to use the formula for the sine and cosine of the half angle, which we have derived in the previous class. So this is what we had derived for the sine and cosine of the half angle. So if we take the ratio of sine A by 2 with cos A by 2, we are going to get tan A by 2. So that is what we can put here. This can in fact also be written as C upon cos A by 2 by sine A by 2 plus cos B by 2 by sine B by 2. And here then we are going to put these formulas. So from here we can see that cos A by 2 upon sine A by 2 equals square root of s into s minus a upon s minus b into s minus c. So this is what, so we are going to basically replace this by this right hand side in this equation, and then we also need to find the value of cos b by 2 divided by sine b by 2. So, again we divide cos b by 2 divided by sin b by 2 and we get cos b by 2 over sin b by 2 equals square root of s into s minus b over s minus a into s minus c. So, we will use this right hand side for this expression in our equation. So, what we get finally is that r is equal to c upon square root of s into s minus a upon s minus b into s minus c. So, this is the first ratio plus square root of s into s minus b divided by s minus a into s minus c. And let us multiply and divide both the numerator and the denominator with square root of s into s minus a into s minus b into s minus c. So, we multiply that in the denominator also, s into s minus a, s minus b into s minus c. And remember that this square root of s into s minus a into s minus b into s minus c is nothing but the area of the triangle. So, the numerator becomes c times the area upon, and then we take this inside the bracket. So, what we get there is s into s minus a plus s into s minus b, that is equal to c delta upon s into 2s minus a minus b. So, finally, we have got the expression for the radius of the inner circle, which is r is equal to c delta upon s into 2s minus a minus b. But what is this thing? We know that 2s is equal to a plus b plus c, and therefore, it is clear that this is equal to c from here, and then this c and this c would cancel, and therefore, what remains is that the radius of the inner circle is equal to the area of the triangle divided by the semi perimeter. So, this is the formula for the radius of the inner circle of the triangle ABC. So, we will derive some other expressions also for the in radius of a given triangle. So, just in the previous slide, we have seen that the in radius is equal to area of the triangle divided by the semi perimeter S. We will now show that this is in fact also equal to S minus A times tan A by 2, which is equal to S minus B tan B by 2, which equals S minus C tan C by 2. So, we will show this now. So, to show this, so we realize that from the Hero's formula, the area of a triangle equals square root of S into S minus A into S minus B into S minus C. If we use this expression here, we have r equal to, so we divide this by s, we then get r equals s minus a into s minus b into s minus c upon s. So, to prove the first equality, we take s minus a so we multiply and divide this right hand side by s minus a, we then get r equals s minus a times. So, the s minus a in the denominator, so this s minus a comes here, the s minus a in the denominator, when it goes inside the square, it becomes, when it goes inside the square root, it becomes s minus a square, and therefore we get s into s minus a. If we recollect, we have already seen the expression for the tan of the half angles of a triangle, and if we remember, then tan a by 2 is sin a by 2 upon cos a by 2, and sin a by 2 is square root of s minus b into s minus c upon bc. Cos a by 2 is square root of s into s minus a upon bc, and when we take the ratio, we see that tan a by 2 is equal to this divided by this, which is square root of s minus b into s minus c upon s into s minus a. And this expression is indeed same as this expression here. So, we can see that this and this are indeed the same, and therefore, this r is equal to s minus a times tan a by 2, because this is tan of a by 2. So, that finishes the proof of this equality. In a similar manner, starting from here, if you multiply this by s minus b and divide it by s minus b, then similarly if we proceed further, then we can show this equality. Again, starting from this equation, if we multiply and divide by s minus c, just like we did for the first equality, then we can prove this third equality here. There is yet another expression for the in radius, which relates the in radius to the circumradius, and which is as follows. So, in any triangle, the in radius is 4 times the circumradius times sin A by 2 times sin B by 2 times sin C by 2. So, we will show this also. If we go a few slides back, then we have shown that the in radius is equal to C upon cos A by 2 upon sin A by 2 plus cos B by 2 upon sin B by 2, and then with simple algebraic manipulation, this is equal to C into. So, we multiply both the numerator and the denominator by the product sin A by 2 times sin B by 2 and we get this expression. But this is of the form sin x cos y plus cos x sin y, and we can take this as x and this as y. So, sin x cos y plus cos x sin y is nothing but sin of x plus y, which is sin of A by 2 plus B by 2. So, this is the denominator, but that is equal to sin of A plus B by 2, which is, because the sum of all the angles of a triangle is 180, A plus B is pi minus C, and therefore, this is equal to sin of pi minus C over 2, which is cos of C over 2. You get the expression that the in radius is C into sin A by 2 into sin B by 2 upon cos C by 2. And then we multiply both the numerator and the denominator by 2 sin C by 2, so that the and this we do because if we see, we have to show this equality. So, we already got sin A by 2 sin B by 2 on the right hand side. We need sin C by 2 also, and therefore, I multiplied with sin C by 2. And in the denominator we get, so 2 sin C by 2 cos C by 2, which is sin C. We already know that the circumradius is equal to A by 2 sin A is equal to B by 2 sin B, which is also equal to C by 2 sin C. And therefore, from this equality, we see that C by sin C is tau is the circumradius. So, we use this identity here. So, this becomes 2r, and then we finally therefore get r to be equal to 2 times 2r times and this is what we wanted to show. So far we discussed we have discussed the circumcircle and the incircle, and in addition to these two circles there is another type of circle associated with a triangle which is not very common, but we will encounter it in some of the problems that we solve later, and therefore, I will be discussing it today. So, this circle is called the ascribed circles, and please note this S over here, ascribed circles of a triangle. The reason for this S is that we do not have a unique ascribed circle. In fact, there are 3 distinct ascribed circles of a triangle, and this is not the same as the case of the circumcircle and the incircle, because we know that for any given triangle there is always a unique circumcircle and a unique incircle, but that is not the case with ascribed circles. So, let us see what an ascribed circle means. So, let us suppose that we have this triangle . So, let us consider this triangle A B C, and let us extend this side A B further in this direction. So, then I am showing the extension with a dotted line, and let us also extend this side AC further in this direction. We next consider the exterior angle of the angle B and angle C of the triangle ABC, and let us construct the angular bisectors of so let us say that this dotted line represents the angular bisector of the exterior angle of angle B, and similarly we have to also construct the angular bisector of this exterior angle C, of this exterior angle of angle C. So, both of these angular bisectors are going to eventually meet at some point. So, let us say that they intersect. So, let us say that both of these angular bisectors intersect at some point O, and then from O we drop a perpendicular to this line which is extended from the line AB. So, we drop a perpendicular here from O to this extension, line extension. So, the perpendicular will most likely, so let us say that this is the So, this is the perpendicular from the point O to the extension of the line of the side AB, and let us say that the point of intersection of this perpendicular with this line is the point D. We also drop a perpendicular from this point O to the side BC. So, let us say that the point of intersection of the perpendicular from this point O to the side BC, and the line BC is E. So, this point is E, and then of course, we also drop a perpendicular from this point O to this line, which is extended from the side AC of the triangle. So, let us say that this is the perpendicular, and let us denote the intersection of this perpendicular with the extended line AC by the point F. And we will now consider two triangles. So, let us start with the triangle BOD and the triangle BOE. So, for both these triangles, what we see is that they have a common side OB. The angle BDO is equal to the angle BEO. Since both of them are 90 degrees, they are equal. And also, because this red dotted line is an angular bisector, it follows that this angle DBO is equal to the angle EBO, and both of them are equal to both of them are equal to pi minus B over 2, because this is angle B, and therefore, this entire angle is pi minus B, and then this angle, because this red dotted line is a angular bisector, this half angle is pi minus B over 2. So, therefore, this angle and this angle are also equal, and hence from basic high school geometry, it follows that these two triangles are congruent. And since they are congruent, it immediately follows that OD is equal to OE. So, OD is equal to OE. In a similar manner, we also consider the other two triangles, which are triangle COE and triangle COF. And as we can see again, both these triangles, so triangle COE and triangle COF, have this side OC as common. Further, this angle and this angle are equal to 90 degrees. So, these two angles are equal, and since this red dotted line is an angular bisector of the exterior angle C, it also follows that this angle and this angle are also equal, and therefore, just like as before, triangle COE is congruent to the other triangle COF. And because they are congruent it follows that OE is equal to OF. And therefore, what we see here also is that OD, OE and OF. So, OD, OE and OF are all of equal length. So, please note that this figure is not drawn to scale. So, they might not be appearing to be equal, but mathematically they are all of equal length. And therefore, also that since we have 3 points here, point D, E and F, and these points are not collinear, it follows that there exists a unique circle such that all these 3 points D, E and F lie on the circumference of that circle. So, let me draw that circle, a part of that circle. That circle is most likely something like this. So, I have only shown a part of the circle, and this circle is called the ascribed circle opposite to angle A. So, this circle is called the ascribed circle. So, this is the ascribed circle to the triangle ABC, which is opposite to angle A. And similarly, if instead of extending the line AB and AC, if we had extended the line CB and CA and then made a circle here, then that particular circle would have been called the ascribed circle opposite to angle C. And similarly, if we extend BA and BC, then we have another ascribed circle here, which is the ascribed circle opposite to angle B. So, therefore, a triangle has 3 ascribed circles. Now, for the ascribed circle opposite to angle A, from the figure we know that OD, OE and OF are all equal, and therefore, this point O must be the center of the ascribed circle opposite to angle A. It has to be the center. Our next objective is to find an expression for this radius. So, for this radius which we denote by R1. So, we would like to find an expression for the length of this radius R1 of the ascribed circle opposite to angle A. So, in order to do that, what we immediately note is that we'll consider the two triangles BOE and COE. So, we will consider the triangles BOE and the triangle COE. We know that this OE is also the radius of the ascribed circle opposite to angle A, and therefore, even this distance or this length is R1, and in fact, this also is R1. If I look at the triangle BOE, then what we see is that because this red dotted line is the angular bisector of the exterior angle B, we know that this particular angle, the value of that angle is pi minus B over 2. And therefore, tan of pi minus B over 2 equals R1 over BE. And similarly, if we consider the triangle COE, so COE, where we know that this angle, the value of this angle is pi minus C over 2, and therefore, in the triangle COE, tan of pi minus C over 2 equals R1 by CE. Now, from this first equation, we have BE to be equal to R1 divided by tan of pi minus B over 2 that is from this equation here, and from this other equation we have CE equals R1 over tan of, so this is tan of pi minus C over 2. So let us move on to the next slide. So what we have shown so far is that BE is equal to R1 over tan of pi minus B over 2, and CE is R1 over tan of pi minus C over 2. So this is what we had. So both those equations follow from here essentially. But we also see from this figure that the sum of BE and CE is nothing but BC, which is equal to A, and therefore if we add these two we get A is equal to BC plus CE, which is equal to, and this can be further simplified a little bit because we know that tan of pi by 2 minus theta is equal to cot of theta. So this is exactly equal to R1 divided by cot of B over 2, and this is equal to R1 divided by cot of C over 2. So we put these expressions here instead of in the place of B and CE, and then what we get is that A is equal to R1 times 1 over cot B by 2 plus 1 over cot C by 2, which is equal to, therefore A is equal to R1 into tan B by 2 plus tan C by 2, from which it follows that the radius R1 of the ascribed circle opposite to angle A is given by R1 equals A upon tan B by 2 plus tan C by 2. And here again we need to, since we already know from the previous lectures that we know the relation between the sine and cosine of the half angles to the lengths of the sides of the triangle. So we are going to use that over here. So we know that tan of B by 2, so tan of B by 2 is sine B by 2 divided by cos B by 2. So if we use these expressions for sine B by 2 and cos B by 2, then we get tan B by 2 as equal to square root of S minus A into S minus C divided by S into S minus B, and we get a similar expression for tan C by 2. So for tan of C by 2 we get it to be equal to square root of S minus A into S minus B divided by S into S minus C. So now we are going to use these two equations instead of tan B by 2 and tan C by 2, and then what we finally get is that R1 equals A upon square root of S minus A into S minus C upon S into S minus B plus square root of S minus A into S minus B upon S into S minus C. And then, as we did in the for the case of the in circle, we are going to multiply and divide. So, we are both going to multiply both the numerator and the denominator by the area of the triangle. So, the numerator becomes A delta divided by, but we know that delta is equal to S into S minus A into S minus B into S minus C. So, this is the expression for the area of the triangle in terms of its sides. So, delta is equal to this, and therefore, it is fine because we have multiplied both the numerator and the denominator with the same quantity, that times this thing. Which is equal to, and then we move this thing inside the square brackets. So, the first term becomes S minus A into S minus C plus S minus A into S minus B, which can be further simplified to R1 equal to A delta upon. So, S minus A is common, we take it out, then we get 2S minus B minus C, but 2S, so 2 times the semi perimeter is equal to the perimeter, which is A plus B plus C, and therefore, this thing is equal to A, which gets cancelled with the A in the numerator, and what remains is delta upon S minus A. So, therefore, this is the final expression that we have here. The radius of the ascribed circle opposite to angle A is equal to the area of the triangle divided by S minus A, where S is the semi perimeter of the triangle ABC. And similarly, so let R2 denote the radius of the ascribed circle opposite to angle B. Then it can be shown that R2 is equal to delta, or the area divided by S minus B, and similarly the radius R3 of the ascribed circle opposite to the angle C is equal to the area divided by S minus C. So, this with that we will conclude this lecture, and in the next lecture we will solve some problems on whatever we have learned so far, and after that we will discuss some more properties of triangles. Thank you.